We present in this video an overview of the Dreams resource management system. We focus on the fault-tolerant services to support permanent core failures, and we highlight its use on a case study. This is a joint work between the partners Onera, Talus, TUKL and UCGen. We first detail how the Dreams resource management works in a nutshell. The Dreams middleware is in charge of ensuring strong temporal and spatial partitioning, which is done with the Stratum hypervisor, and of supporting adaptation strategies to deal with unpredictable environment situations. We consider in particular permanent core failures, which could result from various phenomena such as external fault leading to a processor misbehavior or aging. To support these failures, we implement local and global reconfiguration strategies. Any reconfiguration is pre-computed offline. The reconfiguration mechanisms are implemented on top of Stratum. The stakeholders of the Dreams resource management are the GRM, Global Resource Manager, which is in charge of managing the overall platform. It knows at any time the configuration of all the nodes and switches. The local resource managers are in charge of a node. They consist of MAN services that collect the status of the cores and an LRM which takes local decision if any and applies any GRM request. Let us have a look on a local and a global reconfiguration on a node composed of two cores. In the figure above, the first major cycle, or MAC, is the initial configuration. In this configuration, two partitions P0 and P1 execute. A MAN partition checks on each core its status. At the end of the MAC, two synchronous LRM, among which one is the master, assess reconfiguration is needed. During the second MAC, the core 0 fails, which is detected by the MAN of core 1. The LRM at the end of the MAC takes a local reconfiguration and reallocates partition P0 on core 1, as can be seen on the third MAC. In the figure in the middle, the first MAC is the initial configuration. During that MAC the GRM requests the LRM to reconfigure because a node elsewhere has failed. During the second MAC, application P3 is hosted on the node. Finally, the complete symmetric local reconfiguration graph is shown. C1 is the initial configuration. Plain arrows show local reconfiguration and occur when a core fails. Dashed arrows are GRM reconfiguration requests. In that example, only one global reconfiguration is allowed from the initial configuration and corresponds to the figure in the middle. We show a full scenario of reconfiguration on the following example. The platform consists of two nodes, one T4240 with 12 cores and a Dreams harmonized platform with 2 cores. The nodes are connected through a TT Ethernet network. Stratum executes on each node. The local resource elements, MAN, LRM and LRS, execute on each node as well. The GRM executes on the harmonized platform. Two applications must be hosted, a critical application ROSIS which is a longitudinal flight controller and a best effort application a MPEG server. Let us now show how to generate the reconfiguration graphs via the Dreams toolchain. We remind that we must first model the use case in the Dreams autofocus tool and extract an initial configuration from XConcrete. Let us now have a look to the use case model in the Dreams autofocus. The application is composed of MPEG server and ROSIS. The two Dreams local resource management services. MPEG only contains one task. ROSIS contains 11 tasks. The T4240 middleware contains 12 MAN, 12 LRM that communicate with the GRM. The platform is composed of the T4240, the DHP and TT Ethernet network. If we look at the timing properties, we can see the period of the tasks. For example, altitude hold has a period of 0.02s. The initial partition slot generated by XConcrete is stored in the system schedule. We generate the grec input. Grec is based on constraint programming and on IBM OPLCPlex tool. apps.dat is the generated input. We recognize the number of nodes and applications, the list of tasks and the initial 77 slots. In the OPL code, the list of jobs on the Mac is pre-computed and two decision variables must be found. Start indicates when a job starts while P indicates in which partition. The constraints stipulate, for instance, that a job must execute between its release and deadline. Only one application can use a partition. In the case study, we assume that only the T4240 can fail. Since it contains 12 cores, there are 4096 failure combinations and thus configurations. However, Greg computes in 25 minutes that only 78 plans are needed for reconfiguring the applications. The initial configuration allocates ROSes on the first core and MPEG server on the second core. Extratum and the resource management services are not completely ported on the T4240. We thus show part of the local reconfiguration execution on the Dreams harmonized platform. We can observe the initialization phase of all services and tasks. 6 partitions are created, 1 critical app for ROSys, 1 normal app for MPEG server, 2 LRM and 2 Monday. Initially ROSys executes on core 0 while MPEG server executes on core 1. The initialization occurs during plan 0, then the nominal execution runs during plan 1. At the 11th MAF execution, core 0 fails 0 and LRM applies a local reconfiguration which consists in reallocating ROSys on core 1 while MPEG server must be hosted elsewhere. This is the plan 2.